In this problem, we have a pin that has mass of 0.2 kilogram and it is constrained to move in this smooth curved slot. The shape of the slot is given by this function right here, r, which is the radial distance as a function of angle theta. The motion is controlled by an arm that rotates, the arm OA that rotates. It has a constant clockwise angular velocity of 3 radian per second. So as you can see, by definition, counterclockwise is a positive direction for theta. Therefore, a clockwise rotation will have a -3, negative angular velocity. Theta dot is the time derivative of angle theta, which is the angular velocity. So we need to determine when theta equals to 0 degree, what is the force that arm OA exerts on the pin. Motion is in the vertical plane, which means that we do need to consider weight. So we can draw a quick free body diagram. At angle theta equals to 0, the armed slot is here. So the pin is right here, subjected to its weight force, and then a force from the arm, which is always normal to the arm, as well as a normal force from the slot. In this case, the normal force will be in this direction. And then the radial direction, AR, is in this direction, and a theta, the transverse direction, is here. Okay, so let's translate that graph over here. So weight force W, normal force, force from the arm, and then a R and a theta. So if we can determine a theta and a R at this point, then we can use Newton's second law to determine not only force F, but also the normal force N as well. Normal force N is the force exerted by the slot to the pin. So we can use the formula AR equals to R double dot minus R theta dot squared, and a theta equals to R theta double dot plus 2 times R dot theta dot. So what we know is R equals to 0.6 cosine 2 theta, as well as theta dot equals to -3, which means that theta double dot equals to 0. And we know that theta equals to 0 degree, which is the same as radian, 0 radian. So now we need to find R dot as well as R double dot. So R dot equals to dr dt, which is dr d theta times d theta dt. Chain rule from calculus. So dr d theta equals to 0.6 times 2 times negative sine 2 theta. So that's negative 1.2 sine 2 theta. D theta dt, this part right here, is the angular velocity, and that simply equals to theta dot. So that's R dot. So R double dot equals to dr dot dt. And because R dot is the product of two functions, both functions are functions of time. Therefore, we're going to use the product rule from calculus. So this becomes, first, keep the, actually let's pull out the constant negative 1.2. So within the parentheses, first we have d sine 2 theta dt times theta dot, keep that the same, plus sine 2 theta, keep that the same, times d theta dot dt, which equals to negative 1.2. We're going to use chain rule again. This becomes d sine 2 theta d theta times d theta dt, theta dot, plus sine 2 theta. D theta dot dt simply equals to theta double dot. So in this case, this becomes negative 1.2. D sine 2 theta d theta equals to 2 times cosine 2 theta. D theta dt equals to theta dot multiplied by another theta dot, that is theta dot squared plus sine 2 theta theta double dot. So now we have derived the general equation for r dot and r double dot. So even if the problem doesn't ask us to solve for the force at theta equals to 0, if it asks us to solve for when theta equals to, for example, third pi or sixth pi, we still can use the same approach to solve the problem. So that's why we always want to derive a general equation. So now let's evaluate. Because in this problem, our force F is in the same direction as our weight W. They're both in the theta direction, and the normal force has no component along the theta direction. Therefore, for this particular problem, we don't have to worry about AR. We only need to find a theta. If the angle is not theta equals to 0 degree, then we do need to evaluate AR as well. But in this special case, we only need a theta, which equals to r theta double dot. Theta double dot is always 0. So this is always 0. And then this equals to 2 times r dot theta dot. Don't forget, r dot equals to negative 1.2 sine 2 theta. When theta equals to 0, sine 2 theta equals to 0. So in this case, a theta simply equals to 0. The resultant force along the theta direction equals to negative F minus W equals to negative F times minus mg, that equals to 0. Therefore, you can solve for F from here equals to simply negative mg, which equals to negative 0.2 kilogram times 9.81 meter per second squared, which is negative 1.96 Newton. So actually that solved this problem. This is a relatively simple problem because of the special angle that theta is only 0 degree. But even if theta is not 0 degree, you should be able to solve it by evaluate a theta and AR at the specified theta value, and then use Newton's second law, do force analysis, and then solve for unknown forces. In this case, this negative sign indicates that the direction of the force F is negative theta direction, which is downwards.